unshare my screen. Yeah.
Yeah. So we now have Debangshu Mukherjee. She will talk on from 2D droplets to 2D young males. So Debanshu, I will remind you after 9 minutes. Is that okay?
Yes. Am I audible, Prasanta?
Yes, you are audible. It's visible clearly.
Okay.
Full screen. Yeah, please start.
So let me start by first thanking the organizers for giving me this opportunity to present my work here. And I would also, in fact, try to applaud Alok and his entire team for bringing together this in such difficult times. So I'll be talking about my recent work, the droplets to the angles, which was done with a couple of colleagues, Orko and Nico, and my mentor, Professor Shouvik Datta at IIT. So, sorry. Okay. So the interplay between unitary matrix quantum mechanics and 2D angles is well known and quite old. And this is how the partition function of 2D angles theory look like with the underlying gauge group SUN on a generic Riemann surface with genus G. And as you can see, it's written as a sum over representations. And every representation, so I will actually talk about two very popular examples of connecting these unitary matrix quantum mechanics and 2D angles. So in this sum, every representation can be mapped to a state of energy C2R, where C2R is the quadratic Casimir associated with the representation. So what Minahan and Polychronikos did in 93 was they mapped these states to string states, 2D string states, which wind around one compactified spaceship direction. And they wrote down a Hamiltonian for these string states, which turned out to be exactly same as the Gas-Javicky Hamiltonian, which I will talk about at some time, which comes up in the study of unitary matrix quantum mechanics. Another very popular example is the work of Gross and Matitsin in 95, where they started with the partition, the same 2D angles partition function, and in the large n limit, they looked at the equations of motion, which they interpreted then as a Hamilton-Jacobi equation. And once they wrote down the classical Hamiltonian, that also turned out to be the same as the So we are trying to explore this connection further, and we will take, however, a bottom-up approach. So starting from unitary matrix, so my main goal is over the next few minutes to show to you that starting with this unitary matrix quantum mechanics, I'm going to quantize the system, and I can construct transition amplitude and higher point amplitudes for a variety of 2D angles. So this variety is important. And in fact, it seems to us that the Hilbert space of this quantized unitary matrix quantum mechanics seem to contain a large volume of information about the partition function and all higher point amplitudes of angles, of 2D angles. And as a matter of fact, even amplitudes of Q-deformed angles theories can be constructed using our proposals. Okay, so the starting point is obviously the 0 plus 1D unitary matrix quantum mechanics that you see here. This is the partition function, and this system can be mapped to a collective field theory of real bosonic fields, the field being rho, which is the eigenvalue distribution of the matrix U, and pi being the corresponding conjugate momentum. So, of course, the equation of motion that follows from this Hamiltonian, it's non-linear, it's coupled, and of course, we can handle. But what one can do is you can define this nice this nice variables p plus and p minus as here in this equation. And what this does is it decouples your equation. I mean, just non-linear, but it at least becomes a bit more practical. Now, there is an alternate view of looking at this p plus p minus. So what you can define is, you can define, I'm not sure if one can see, so this y-axis is what I'm calling the p coordinate, the x-axis is the theta coordinate. And you can define a sort of density here, which I'm calling var phi, which is essentially a theta function. Which so in this adjoining diagram, if you see, we have a area in this p theta plane where this upper and lower surface are essentially characterized by these two curves, p plus and p minus. And the integral of over dp gives you the density, and times this gives you. So these are precisely the droplets that I'm going to talk about. And so this is basically the classical picture. And in terms of, so various large n phases of these unitary matrix quantum mechanics, in essence, can be characterized by the shape of these droplets. So how they look like. And naturally, the evolution of these droplets also tells us about the evolution of the first.
We have lost him probably.
Sorry? Hello?
Debanshu?
Yes?
Yeah, I think because you're moving back and forth, so your voice is actually breaking. So
is this better?
Okay, yeah, that's okay. Now it's okay.
Okay. So eventually the Hamiltonian, in terms of these P plus and P minus variables, take this form that you see here. And because of the original theory having a U going to U dagger symmetry, the area of this droplet is constant. So a natural thing to do would be to quantize the system. And in order to quantize this system, we first start by regularizing the total number of states in the phase space like this. As it tells you that I'm dividing the phase space into unit volume, with each volume being and this is a classical limit is a double scaling limit between n and h such that the product is equal to 1. So if you want to reproduce the correct equations of motion, you have to impose. And this is how I describe my fluctuations in terms of these functions p tilde. And once we quantize the system, this is how the commutator of p tilde plus minus looks. Decomposing these into Fourier modes in the theta direction, what we see is that the modes A and B corresponding to this P plus and P minus follow abelian Cash-Moody algebra, and the full Hamiltonian actually breaks down into nicely two chiral sectors, H plus and H minus. So this plus and minus basically corresponds to, so this plus and minus corresponds to fluctuations in the upper Fermi surface and the minus to the lower Fermi surface. So you also have a H minus, which will be essentially this A replaced. And as you can see, the Hamiltonian divides into three parts, one part being a constant. This part is V theory, which looks like harmonic oscillator, and you have an interacting cubic piece. So in order to construct the Hilbert space, we first define the vacuum like this. And a generic excitation above the ground state is essentially a bunch of A daggers and B daggers hitting the vacuum. And of course, even the full Hilbert space also decomposes nicely. Now, the catch here is that this K state that we have just defined, they are not eigenstate, they are only eigenstate of the free part of the Hamiltonian. So it's eigenstate of only this part, not of this. And the expectation value of P plus in this K state goes like this, where again, this is the classical value, and you have this H contribution coming. And so physically speaking, this K states characterize ripples over these spaces. Also, by the way, I should point out, so from now on, we will only focus on one sector, only the H plus sector, because as you can see, the Hilbert space decomposes nicely. So all the arguments go through for the negative sector. Now, the things that we will be mostly interested, the thing that will mostly interest us is these coherent states. So these coherent states, this is how we define it. And the expectation value of the P plus operator in this coherent state looks like this. Now, this third term is the one that should grab your attention, because what you see here is that these are essentially characterized odd-one deformations of the classical solution. And in fact, if you calculate the quantum dispersion, you see that it vanishes identically. And this is precisely the reason why we dub such states as classical. Okay. Now, we saw that K was not eigenstate of the full Hamiltonian. So what one can do is associate a Young tableau with these states K. So K is essentially a bunch of these numbers, K1, K2, K3, and what one can do is one can associate a Young tableau thinking like K1 to be the size of number of one cycles, K2 to be number of two cycles, and so on, and define a state in the Young diagram basis, which I'm calling R plus. In the large n limit, if you calculate the eigenvalue, it turns out to be exactly equal to the quadratic acid, which we also saw in the first slide. The same. And this entire Hilbert space structure seems to be very similar to the chiral sector of a UN to P axis. Now, the most important thing is this translating between these two bases, this coherent state and this basis which is written in terms of this R plus states. These coefficients are nothing but the Shouk polynomials, arguments being this tau plus. Tau plus is this data that you give into the coherent state. So now we have the full machinery ready, and in order to write down the transition amplitudes, hello? Hello?
Yeah, we can hear you. It's fine.
Okay. Yeah, go ahead.
Actually, yeah, I got a message here that the internet is not okay. We have the full machinery, and so the first thing is to write down a transition between two coherent states, tau A plus and tau B minus, which is over a time interval. So what you see is exactly using this equation. What one can do is we can write down this amplitude, and it turns out to be exactly same as the cylinder partition function for 2D angles. So the transition amplitude between these two coherent states is identical to the chiral partition function, where the holonomies are identified with this data given in tau A plus and tau B minus. Okay, so now going on, one can choose a very special point in this tau plane where all this these numbers tau that we given to the coherent state in trying to define the coherent state, they can all be 1. And for such a case, the Shoe polynomial actually simplifies simply to the dimension of the representation. So more geometrically speaking, that would mean to choose trivial holonomy on one of these circles. So you can think of closing one of these circles, and what you end up with is a test, which is precisely what you have. You reproduce the disk geometry for the angles theory. And if you do the same for both the sides, you eventually end up with a sphere, which is what you have here. You can.
Debangshu, you spent 10 minutes already.
Okay. Oh yeah. So this is the very similar thing which you saw in the first slide, where so for the sphere genus is 0, so you simply get what I. So now, in order to define generic hard point function, we first define this droplet operator and this density matrix, where this is how we define the probability, which is precisely where the data of the genus goes in. And as we can see that the partition function exactly matches with what I started off with 2D angles, and this is how one can also construct generic endpoint. So this corresponds to basically putting n many holonomies on a Riemann surface of K. Now, the thing is that I also promised something about this Q-deformed angles, which is that so the thing about this Q-deformed angles is that the gauge group itself is Q-deformed. And this is captured by this non-commutativity in the entries of the group element, which is parameterized by this Q. What we do is, however, a bit different. We choose a very special kind of coherent state, and which finally eventually ends up in giving us all the correct disk sphere as well as cylinder amplitude for the Q-deform. So now throughout you must have noticed that I had been working on only one of the sectors, the plus sectors. In order to get because you know the partition function will also get contribution from the propagator coming from the minus sector, we need to join them and glue them up, and this is done by what is known as the composite representation, and this is a diagrammatic way of representing it. R minus this young factor being the one associated with R minus representation. You sort of create anti-boxes here. You then delete this part, finish off this Young diagram, and then you associate this with the Young diagram for the full composite representation R plus R minus. And once the full Hamiltonian acts on this composite state, you do indeed get the quadratic Casimir to be the energy coming from both the sectors to be the full energy of the full system, and even the transition amplitude for the full state is also used. So eventually, so the main upshot of this work is that we have given a geometric prescription and constructed partition function for 2D angles on very generic Riemann surfaces, and it seems to be the case that this quantized Hilbert space on this droplet side contains much more information than we actually expected. It contains information on very generic 2D angle surface and also its Q-deform analog. The system nicely decomposed into two chiral sectors, and we joined them later. And then we eventually defined very special coherent states in order to map the partition function of 2D angles to our unitary matrix quantum mechanics. Now, one thing that we did not explore much is the formation of folds. So we worked with P plus profiles with these upper and lower Fermi surface, which are very nice, single value. And they have been studied earlier. Our next goal is to exactly look at what happens to what do we get on the quantum mechanics, the 2D, what we get for the 2D angle side if we allow for formation of folds or shocks. And also what exactly are the gravity duals of this fold states or shocks. I think I'm out of time, and so let me just leave you with this pathway of our construction. So that's all I have to say. Thank you. I'll like to take a question.
Thank you, Debangshu. We have a question from Somadatta.
Yes.
So Somadatta, please go ahead.
Yeah, so could you go back to your slide where you had the theta function of the P plus P minus?
This one? This one?
Yeah, this one.
Yes.
No, the next one.
This one?
Yeah, this one. So should it be theta of P plus minus
Sorry.
So this theta function,
Yeah.
is it a product of P plus and?
This is the P
There is
theta
a
plane.
minus,
All
is
that I'm
minus?
saying is that when P value is less than P plus, so within this region, it is going to have support 1. That's all I'm saying. Outside, it's identically 0. This theta function is heaviside theta. I mean,
Heaviside theta, yeah.
Normal theta. Yeah, theta of x is 1 when x is greater than 0 and 0 otherwise.
Okay. Alok.
Yeah, hi Debangshu. Hi.
Hey, hi.
So for any for any n, Witten had this quantization of 2D Young-Mills, right? Using equivalent localization. No, I was just wondering if the partition function he computed, is there a nice way to compare with his droplet picture or?
Okay. Thank you for the question. So the thing is that if you notice, this entire droplet picture comes out from a collective field theory, which is inherently a large n business.
Right, but you could do Witten's thing also for large. I mean, maybe if I understand correctly, it was for any n, right? I mean,
yes, exactly.
So
it was for
should a comparison be possible? I mean, okay, maybe I can ask us just a small follow-up that, I think there were these non-perturbative contributions coming from what he identified as unstable solutions of the 2D Young-Mills equation in this. So is there a way in large n at least to identify those solutions in the droplet picture? Or I mean, I don't know if that's the right question.
Okay, this is very speculative, but probably these fold states are these non-perturbative solutions, but we have not, unfortunately, explored. But but this is very speculative, so don't take my word for it. But presumably these fold states. So if this thing evolves, so we have always worked with P plus to be single value, right? So you can have this profile to be going. Is my cursor visible?
Yes, it's visible.
So it can have something like this. So you can presumably that is what will correspond to those class of states.
Okay,
but
thank you.
Again, this is speculation.
Okay. I will talk to you later.
Yeah.
Okay, Ronak.
Hi, Debangshu.
Hey,
talk.
Hi.
I actually have 2 questions.
Yeah.
First is what the Q in the Yang-Mills side, what is it on the matrix side?
So Q, this?
Yeah, the Q, what does it come from in the matrix side?
On the matrix model side, it's basically the Q deformation. It's a deformation of the gauge group. So it has an inherent parameter in it. So
I see. So
so for example, you consider SU2 for example. So you will have a bunch of it will have entries alpha, beta, gamma, delta. So what you will have is alpha delta will be equal to some Q times beta, Q times delta alpha, and correspondingly for so that's what is on the matrix models.
I see. Thank you. Also, I wanted to just kind of make a comment which is very interesting. This this coherent state that you just wrote down.
Yeah.
The same coherent state the coherent state on the slide that was open just.
Sorry. Which?
With the gamma power n minus gamma power minus n that one.
Okay.
The slide that was open like when you were answering my previous question.
Okay. Yes.
Okay. Yeah. That equation 23. Yes. So this coherent state actually turned up in a. I just checked, and this exact same coherent state turned up in a very different context, which is in studying entanglement in topological string field theory. There was this paper last year by Gabriel Wong, Will Donnelly, and others, and the capital N going. Yeah.
I am aware of that work, actually. Yes, I am aware of that work also. But the fact that this turns up in topological string theory should not be surprising. The fact that somehow entanglement is also involved here. I'm aware of it, but I have unfortunately not explored.
Yeah. Okay. Thanks. I was wondering whether you had any thoughts on that.
Yeah. I know. I don't have immediately any thoughts, but yeah, I'm aware of it.
Okay. Thanks.
Okay. Debangshu, thank you very much for the nice talk. Please stop sharing your screen now.